All right. At this point, we are done with our elementary study of vectors and how to represent them. In particular, we introduced this notion of a basis, and we saw what that does for representation of vectors. We looked at this notion of the summation convention. We also looked at what it does for our representation of dot and cross products. Okay. Now we're going to change gears a little and introduce a mathematical object which may look new at first, but which conveniently has a representation that everybody has seen before. Okay, and in particular, we are going to talk now about tensors. Okay. Tensors are a very important part of continuum physics, especially of continuum mechanics. They can be thought of as a generalization of the notion of scalars and vectors. Alternately, scalars and vectors are particularizations of tensors, right? Okay, what do we mean by a tensor? Here's how we go about it, okay? Let's suppose that we have vectors, right? So let's consider vectors, say u, v, and so on, u, v, w, whatever else you like. And recognizing that these are vectors in three-dimensional space, we are going to write them as belonging to R3, right? They live in three-dimensional space. So we have vectors. Here's one of them, right? And we've seen that in order to talk about this vector in anything like a systematic fashion, it's useful to have a basis. Okay? So we want now to introduce another object related to these vectors. Before we go ahead and introduce this other object, and this object is going to be a tensor, let me also point out one important fact now. We are going to often use the notion that in continuum physics, and definitely in continuum mechanics, a vector is invariant. What we mean is that if we look at this vector as maybe the velocity vector, right, or a force vector, we will describe this vector as being invariant with respect to representation. Okay? What that means is that this vector always stays the same. What may change is how we want to describe it. We may choose to describe it in this basis, or one of you may not like this basis and say, well, for other reasons, I want to use a different basis. Maybe you want to have that basis. Okay? The vector, however, is invariant. You will observe that as I change these bases, the vector stayed the same. I did not move this vector, or at least I tried not to move this vector. I'm trying to convey to you the notion that this vector is invariant. The only thing that will change as we change our basis is what? Think about it for a couple of seconds. The vector is invariant. I change these bases, right? I may start out with this basis, and then I say I don't like this basis. I'm going to use a different basis. Something is going to change. That something is the components of the vector in the different bases. This vector remains the same, but its components in this basis will be different from its components in this basis. Okay? All right? That's an important notion which will become even more important as we get into this other subject, this other topic we're going to look at right now of tensors. Okay? All right. So, consider vectors u, v, and so on belonging to R3. Let me just state what we talked about. Note that a vector is invariant okay, its components can change if the basis changes. Okay? The way we represent this mathematically is the following. So if we choose to consider a vector u, okay? Right? Now, u written in terms of our basis so far would be that, right? That is the representation of u in our basis E, or EI, EJ, EK, all right? If I choose to represent it in a different basis, let's suppose I want to use a different basis that I represent as E bar, maybe, right? I, okay? Maybe I write out the components of u in this new basis as u bar I, okay? What is different is that ui is not equal to u bar I if ei is not equal to e bar I. Okay? Of course, when I say e is not equal to e bar I, what I really mean is that we don't have anything like e1 being equal to e bar 1 and so on, right? E2 is not equal to e bar 2, E3 is not equal to e bar 3. Okay? This is a very important notion, right? And in terms of our props here, we may consider this basis to be we may consider this to be the basis E1, E2, E3, and that to be the basis E1 bar, E2 bar, E3 bar, right? The vector is the same, its components are going to be different. The same idea is going to be very important as we now start talking about tensors. Okay, so I've been saying all this stuff about tensors without telling you what they are. Here's what they are. Suppose we have our vector u, okay? Suppose I have my vector u, and I want to relate it to some other vector which I call v, okay? One way to relate it to v is to say that there exists a linear operator that for now I'm going to denote as a, okay, which carries out some linear operations on u to give me a new vector v. Okay? What I've introduced here, a, is a tensor. Right? It essentially represents a linear operation right? It is a linear operator on any vector, right? It's a linear operator on any vector in three-dimensional space. Okay? Now, just as we write our vectors u, v, and so on as belonging to a space R3, we introduce the notion of a different mathematical space for tensors. Okay? We will say A belongs to a mathematical space. Now, this is not like three-dimensional space. It's a mathematical space that we denote as GL3. GL3 is the group of general linear operators on vectors in R3. The 3 in GL3 refers to the 3 dimensions in R3. Okay? This is a tensor, right? It is essentially a linear operation on vectors. Now, why do tensors matter in continuum physics or continuum mechanics? Obviously, we are going to write certain physical quantities as tensors. You may already know of some quantities, some physical quantities that are tensors. So think about them for a couple of seconds if you can already come up with some. And I will bring up one of them. Okay? So, a particular example of a tensor, the most prominent one in the context of continuum mechanics, perhaps, is the stress tensor. What do we mean by this? Here's what we mean. I'll bring back my prop for my continuum solid body, right? Let's suppose now that on some part of the surface, right, somewhere out here, we decide to impose a traction on it, right, a traction vector. And let's suppose that this arrow is my traction vector, right? It's acting upon this body, all right? So the arrow is my traction vector. Now I have very purposely and carefully applied this traction vector on the body in a non-normal orientation, right? Clearly, and I hope you can see it, this traction vector is acting not normal to the body, okay? However, at this point of action, there is a normal, right? And that normal is that, right? So I have that normal, okay? Let me see if I can do all of this together. Maybe I need to move it somewhere else. Okay, so that's the normal vector. That is my traction, right? So we have two vectors acting at that point. They're not the same. Two vectors acting at a point, but they're not the same. That should immediately make you start thinking about something. How do you go between those two vectors, right? Well, the way you go between those two vectors is the stress. Okay, so the relation between the normal at this point and a traction vector is the stress tensor. Okay, so I'm going to write it out here. Supposing we have our continuum body, and as always, remember, we are representing it by the region it occupies in space, which is omega. We have our basis here, right? The boundary of the region occupied in space by the body is partial omega. As we go ahead, we will interchangeably use the region occupied in space by the body and the body itself. We will sometimes call the body omega itself, which is an abuse of notation, but it gets to be sometimes just convenient to describe it as that. Okay, so what did I say about this? I said let's take a point on the surface and draw a normal vector. Okay, that is my normal vector n, a unit normal, okay, and I have a traction vector acting there, okay. I'm going to denote this traction vector as t, all right. The relation between those two vectors is given as follows: t equals sigma n. Sigma is the stress tensor. Okay, we will study this in great detail, in much greater detail as we get further into our main study of continuum mechanics. We will revisit this idea and develop it more, but for now I ought to also mention that this idea is originally due to Cauchy. Okay. Right, and of course there are many other examples of tensors. We're going to see many of them. One that will come up fairly early is the moment of inertia tensor. Okay, so we will see more of them. All right, so let me just write that down. Also, the moment of inertia tensor. Okay, so that's another example. Okay, so this is why we need to study tensors in continuum mechanics. Let's proceed then by saying some more about this tensor that we've introduced, right? Let's return to our example where we introduced a tensor A. So we return to the example. V equals A U. You note that here too I do have a bar under A, just as I have for vectors. That may initially seem confusing, but as we go ahead we will observed that we can distinguish between tensors and vectors simply by context. Okay, so that's going to be our notation. Okay, what can we say about this, right? We want to be able to say more about tensors just as we could for vectors. We will now, and we will do this by exploiting our basis and our representation of vectors in that basis.